you see these massive structures all around us, right? Like a huge crane lifting something incredibly heavy, or just an airplane sitting on the runway. How does its landing gear actually hold up all that weight?
It's fascinating stuff.
It really is. And it all boils down to this one fundamental idea in engineering: equilibrium.
Exactly.
So today, we're doing a deep dive into rigid body equilibrium. We're pulling out the key ideas from, foundational engineering thinking, trying to give you a shortcut to understanding the hidden mechanics holding things together.
And we'll hit on something interesting, too.
Oh, yeah? What's that?
Well, you might think, okay, more supports must mean more stability, right? Just add more legs to the table.
Seems logical, yeah.
But sometimes having too many supports can actually make a structure much harder to figure out. It can even kind of counterintuitively lead to instability.
Huh. Okay, that's a paradox. We'll definitely have to unpack that one.
We will.
All right, so let's start at the beginning. How do engineers make sure something like a simple ladder or even a whole building frame stays put? How do they achieve this equilibrium?
Okay, so at its core, equilibrium just means something isn't accelerating. It's either completely still, totally at rest, or it's moving at a perfectly constant speed and direction. No changes.
Stable.
Stable, exactly.
Yeah.
And for what we call a rigid body, which is our idealized object to be in equilibrium, two main conditions have to be met.
Okay, what are they?
First, you need force equilibrium. Basically, all the external pushes and pulls acting on the object have to cancel each other out. The sum of all forces equals 0. For phi equals 0 is how we write it.
Like that perfect tug of war you mentioned, where nobody moved.
Precisely. No net force in any direction. The second condition is moment equilibrium. This means all the twisting effects, the moments of those forces, and any pure twisting forces called couple moments, they also have to cancel out around any point you choose. Sora is immersive.
So no net turning or spinning either.
Correct. No translation, no rotation. It's perfectly balanced.
So just to clarify something you said earlier, this constant velocity thing, does that mean like a satellite zooming through space at thousands of miles per hour is technically in equilibrium? That feels weird compared to a bridge just sitting there.
Huh. Yeah, that's a great point. It does feel a bit strange, doesn't it? But yes, from a physics standpoint, constant velocity is equilibrium. The key is zero acceleration, no change in speed or direction.
Okay.
Now, in structural engineering, we're usually focused on that at-rest case, obviously. We want buildings to stay put, but the principle's the same.
Got it.
And what really helps us here is that core assumption you mentioned, treating things as a rigid body.
Right, you said that simplifies things. How so?
Well, all real materials bend or stretch a tiny bit under, steel, concrete, everything deforms. But for most structures we build, these deformations are so incredibly small, they don't significantly change the geometry. So assuming it's perfectly rigid, that it doesn't deform at all, makes the math way easier. The forces keep acting in the same directions. The distances for calculating moments stay the same. It's a hugely valuable simplification.
That makes a lot of sense.
Mm-hmm.
Okay, so if the math relies on knowing all the forces and where they act, how do you even start mapping that out? How do you visualize it?
That brings us to probably the single most important tool in solving these problems. The free body diagram, the FBD.
The FBD, okay.
Honestly, you can't really solve an equilibrium problem without one. It's basically a sketch. You draw the object completely by itself, like you've cut it free from everything around it.
Isolated?
Isolated, exactly. And then on that sketch, you draw every single external force and any couple moments that are acting on that body from its surroundings or, from gravity. It's the absolute roadmap for your analysis. Get the FBD wrong.
And your whole solution is off.
Your whole solution will be wrong, guaranteed.
Okay, so roadmaps is a good word for it.
Yeah.
What are the key rules, then, for drawing a good FBD? What principles do we need to follow?
Right. There are a few key things. First, as we said, isolation. You draw only the body you care about, nothing else. Just cut it away mentally.
Got it.
Second, support reactions. Wherever the object was connected or supported, those supports were preventing some kind of motion.
Yeah, holding it up, stopping it, sliding.
Exactly.
Yeah.
So on your FBD, you replace those supports with the forces or moments that represent that prevention. If a support stopped it moving vertically, you draw an upward force there. If it stopped rotation, you draw a couple moment.
Okay, so the reactions represent what the supports were doing.
Precisely. Third, and this trips people up sometimes, is internal versus external forces. Forces inside the object, like between two parts bolted together. You ignore those on the FBD of the whole object.
Why that?
Because they always occur in equal and opposite pairs within the body. They cancel each other out when you look at the body as a whole. Only external forces from the outside world acting on the body affect its overall equilibrium.
Makes sense. Anything else?
Yep, one more big one. Weight and center of gravity. The object's own weight is an external force caused by gravity. We represent it as a single force acting downwards through a special point called the center of gravity, usually labeled G.
And for simple shapes, that's just the middle.
For uniform shapes, yeah, it's usually the geometric center. It simplifies things nicely. We often use these idealized models too, like a real bolted joint might allow a tiny bit of wiggle, but we might model it as a perfect pin that only allows rotation. Or a bridge support might let the bridge expand with heat, so we model it as a roller. It's about capturing the essential behavior.
Okay, that's a clear set of principles. So let's talk more about those support reactions. You mentioned pins, rollers.
Yeah.
How do these common types actually translate into forces on the FBD?
Good question. Each type of support allows certain movements and prevents others, and that dictates the reaction. So think of a simple cable or maybe a lightweight bar connecting 2 points. It can only pull along its length, right?
Right, like a rope, tension only.
Exactly. So on the FBD, it exerts a single force pulling away from the object along the line of the cable. That's one unknown force magnitude.
Okay.
Then you have things like a roller, or maybe a perfectly smooth surface, or even a pin sliding in a smooth slot. These only prevent motion perpendicular to the surface or the slot.
So they can slide along it freely.
They can slide along it, yeah. So they only exert one force reaction perpendicular to that surface or slot direction. Again, just one unknown.
Okay, one unknown force.
Now, a smooth pin or a hinge, think of a door hinge. It stops the door moving sideways or up and down, but it lets it swing, right? It allows rotation.
Yeah.
So it exerts two force components. Usually we draw them as horizontal, Fx, and vertical, Fey. It prevents translation in any direction in that 2D plane. So two unknowns there.
Two unknowns. Got it.
And finally, the most restrictive common type is a fixed support. Think of a flagpole cemented into the ground. It prevents any translation, horizontal and vertical, and it prevents rotation.
It's completely locked down.
Completely locked. So it exerts two force components, Fx and phi, and a couple moment m to resist that rotation. That's three unknowns from one fixed support in 2D.
Wow, okay, so the type of connection is absolutely critical for setting up the problem.
It's everything for the FBD.
Now, this is mostly 2D thinking. What happens when we go to the real world, 3D structures? Does it just get way more complicated?
It does add complexity, yeah. In 3D, an object can move along three axes, X, Y, Z, and it can rotate about each of those axes too, so potentially more reactions.
Okay.
Take something like a ball and socket joint, like your shoulder joint maybe, or in engineering, maybe connecting parts of heavy machinery.
Right, allows lots of movement.
It allows rotation freely in any direction.
Yeah.
But it prevents translation along all three axes. So on the FBD, a ball and socket joint provides three force reactions, Fx, Fe, Fc, but no moment reactions.
Okay, three forces, no moments. Interesting. What about other 3D supports, like bearings or hinges in 3D?
Right, things like single journal bearings or certain types of pins and hinges in 3D can, in theory, resist both forces and moments. However, and this is a really useful simplification engineers often use, if you have a shaft supported by, say, two properly aligned bearings, often the bearings working together prevent rotation just by their force reactions alone. The couple moments they could exert become kind of redundant, unnecessary for equilibrium. So we can often neglect those potential moment reactions at the individual bearings if they are properly aligned in pairs or groups.
Ah, so the system setup can simplify things.
Exactly. It depends on the overall configuration.
Okay, so once we've painstakingly drawn this perfect FBD with all the right forces and moments based on the supports, then what? How do we actually solve for those unknown reaction forces?
That's where the equilibrium equations we talked about earlier come back into play. For a 2D problem, where everything lies flat on a plane, we have those three fundamental equations. First, the sum of all force components in the x direction must be 0. Fepric equals 0. Second, the sum of all force components in the a direction must also be 0. Fep equals 0. And third, the sum of all moments about any chosen point O must be 0. Fepl equals 0.
Any point. Does it matter where I choose O?
That's a key strategic decision. You can sum moments about any point, but choosing wisely makes life much easier.
How so?
Well, think about it. The moment of a force about a point is 0 if the force passes through that point, right?
Right, because the distance, the moment arm, is 0.
Exactly. So if you cleverly choose your point O, where the lines of action of, say, two unknown forces intersect.
Then those two forces don't appear in your moment equation.
Precisely. They create no moment about that point. So your Momo equation might suddenly only have one unknown left in it. Maybe the third unknown force or an unknown couple moment. You can solve for it directly.
That's clever.
Yeah.
It's like picking the perfect pivot point to isolate what you want to find.
It is. It turns it into a bit of a puzzle, finding the smartest way to apply the equations.
Okay, that makes sense for 2D. 3 equations typically solve for 3 unknowns. What about 3D then?
In 3D, because you have forces and moments along in about 3 axes, x, y, z, you get more equations. You get 6 independent scalar equations, 3 force equations, Fx, 0 Fx equals 0, 0, Fs equals 0, and 3 moment equations, F of x is 0, MAA equals 0, and z equals 0. These represent summing moments about the x, y, and z axes, respectively.
6 equations. So in 3D, you can potentially solve for up to 6 unknown reaction components, forces, or moments.
That's generally the case, yes. It gives you a complete toolkit to analyze forces and moments in all 3 dimensions.
It really is like a full diagnostic system. Now, what if you do all the math, you set up your equations, you solve them, and you get a negative answer for one of the forces? Does that mean you messed up the FBD or something?
Not necessarily. That's actually a really common thing to happen, and it doesn't usually mean an error in the method. If you calculate an unknown force or moment and the result is a negative scalar value, it simply means the actual direction of that force or the actual sense of that couple moment is opposite to the direction you initially assumed when you drew it on your FBD.
So you just guessed the direction wrong initially.
Exactly. You assumed it was pushing up, but it's actually pulling down. Or you assumed clockwise moment, but it's really counterclockwise. The math corrects your initial assumption. You just note the correct direction and use the positive magnitude. No big deal.
Okay, that's good to know. So negative signs aren't errors, just corrections to your initial guess.
Correct.
You know, sometimes looking at complex structures like trusses or machine linkages, some parts look really simple, just straight bars connecting 2 points. Do those have special properties?
Oh, absolutely. Recognizing these special cases can be huge time savers. We call them 2 force members and 3 force members.
Okay, 2 force members.
Yeah, if you have a component like a bar or a link, and it's only subjected to forces at 2 points, and usually we ignore its weight or assume it's negligible.
Like that cable example earlier. Or maybe a hydraulic cylinder pushing between 2 points.
Exactly like those. For that member to be in equilibrium, those 2 forces must be equal in magnitude, they must be opposite in direction, and critically, they must act along the same straight line connecting the 2 points where the forces are applied.
So they have to be pulling directly apart or pushing directly together along the line of the member.
Precisely. Knowing this is powerful because you instantly know the direction of the forces acting on or by that member. It removes one unknown, the direction right off the bat.
That does seem like a useful shortcut. And 3 force members.
Similar idea. If a member is subject to exactly 3 external forces, again, often neglecting weight, for it to be in equilibrium, something specific must be true about how those forces are arranged.
What's that?
The lines of action of those 3 forces must either all intersect at a single point, we call that being concurrent, or all 3 forces must be parallel to each other.
Concurrent or parallel? One or the other.
It has to be one or the other for equilibrium. If you spot a 3-force member, knowing this geometric constraint can sometimes let you solve for forces using trigonometry or geometry instead of writing out all the fucking equations. It can really simplify things.
Yeah, I can see how recognizing those patterns would speed things up significantly, avoids unnecessary calculations.
Definitely. Experienced engineers look for these instinctively.
Okay, this brings us back around to that paradox we mentioned at the start. The idea that maybe more supports isn't always better.
Right. This gets into the concepts of determinacy and stability.
Okay.
So a structure or a body is called statically determinate if it has just enough supports to keep it stable and prevent any rigid body motion. And D, if all the unknown reaction forces can be found using only those equilibrium equations we've discussed. The 3 in 2D or 6 in 3D.
It's perfectly balanced, just the right amount of constraint.
Exactly. Now, what happens if you add more supports than are strictly necessary to prevent motion?
Like putting an extra leg on a 3-legged stool, it already stands up fine.
Perfect analogy. That extra support is providing what we call a redundant constraint. The structure now has more unknown reaction forces than we have independent equilibrium equations.
Ah, so beat sealers and name pounds aren't enough anymore.
They're not enough to find all the unknowns. We call this situation statically indeterminate. The structure might seem more stable, but you can't solve for how the load is distributed among all those supports using just basic statics.
So how do engineers deal with those?
That requires more advanced analysis. You have to start considering how the material deforms under load, how much that extra leg compresses compared to the others, for instance. That's a whole other field, mechanics of materials. So adding supports can make the analysis much more complex.
So more isn't always simpler. It can actually be harder to analyze.
Precisely the paradox. But there's another potential pitfall, too, even if you have the right number of supports.
Oh.
Yeah, it's called improper constraints. This is where the supports are arranged poorly, so even though you might have, say, 3 unknown reactions for 3 2D equations, the body is still unstable.
How can that happen?
2 main ways. One is if all the reaction forces are concurrent. Imagine a beam supported by a pin and a roller, but the roller surface is angled so that the rolling force points directly at the pin.
Okay.
All the reaction forces now pass through that single pinpoint. What can the beam do?
It could spin around the pin.
Exactly. It's unstable against rotation about that point, even though the forces might technically sum to 0. The constraints are improper.
Wow. Okay, so concurrent reactions are bad. What's the other way?
The other is if all the reaction forces are parallel. Imagine trying to support a beam using only vertical
I
rollers.
could just slide sideways, right?
Perfectly put. There's nothing to stop horizontal motion. So even if you have the right number of reactions, if they're all parallel, the body is unstable in the direction perpendicular to those forces. Again, improper constraints.
So it's not just about the number of supports, but also their arrangement. They have to be arranged correctly to prevent all possible motion and rotation.
That's the key takeaway. Proper constraint is crucial for stability.
And tying this back to the real world, this is fundamental to everything, isn't it? Designing a crane that won't tip, making sure a bridge stays up, even figuring out the best way to load a wheelbarrow so it doesn't flip or put too much strain on you.
Exactly right. That wheelbarrow example is great. An equilibrium analysis, drawing that FBD, can tell you exactly how the forces change depending on where you put the load. It's incredibly practical stuff. Every stable structure is a physical demonstration of these principles working correctly.
It really makes you appreciate the engineering involved. Okay, so let's recap. We've journeyed through the core ideas of rigid body equilibrium, defining the conditions, mastering the all-important free body diagram, applying the force and moment balance equations,
Looking at those handy shortcuts with 2 and 3 force members.
and crucially, understanding this interplay between constraints, determinacy, and stability. Knowing when you have enough support, when you have too much for simple analysis, and when it's just plain unstable.
And hopefully, understanding these principles gives you a new lens to see the engineered world. It's not just about abstract equations. It's about the physical forces that shape our reality and how engineers cleverly manage them to keep things safe and functional.
Definitely. So here's a final thought to leave you with. Next time you see a large airplane on the ground, look closely at its landing gear. Notice the specific number and arrangement of the wheels. Why that configuration? Why, for instance, don't they just stick an extra wheel way out at the tail for, extra support? Considering what we've discussed about redundant constraints and statical indeterminacy, what might adding that extra wheel imply about the complexity of ensuring everything is properly supported? Something to think about.